Yes, you're going to be graphing sinusoids. We're going to talk about just graphing sine and cosine functions. And those are the only two we're going to stick to today, but they're actually going to be functions. You can see a picture of one on page 384. That's a picture of a sine function. You've probably already seen that before. When we did 12 basic functions, those were two of them. Good with that. And we're going to see how those things are generated today, and then you are going to graph sines and cosines that are transformed all over the place. But you're very familiar with transformations, or you should be. So the first thing I want to get you familiar with is just graphing a plain old sine function. What it means and how you interpret it and all that kind of stuff. I hope those of you over there can see through that ladder to this. Can you see this? You can be able to see it? Okay. So this is the deal. This right up here is going to, what we're graphing is y equals sine x. So that means the y-axis is the value of the sine of x. Well, I put that pretty high. This is x. If you want to call this something else so that it's really makes you believe that it's an angle, you want to call it x, that's fine. If you call it the sine of theta, then this is the theta axis. Doesn't matter. Whatever goes on this axis when you're graphing a trig function is an angle. These are angles that go along here, okay? And we are going to graph ours in radian mode, because if we did it in degree mode, we could do it, but it's really contrived and difficult. And I know you won't. But radians have got pi in it. It's okay. It's going to be better. You're going to like it better. Okay? So here's how we're going to generate this. We're going to go back to the unit circle, which you are familiar with for graphing angles, or you should be. Those of you who haven't done your homework might not be as familiar with it as you should be. If I draw that diameter right there, then what I'm going to do is I'm going to go split this circle up into 8 equal pieces. Here's 4 of them. I'm going to split it up into 8. What size will the angles be? 45. So that's where I'm going to start. As I go around the circle, I will graph the others. So this thing right here, this 45 degrees, in other words, pi fourths, that's what I'm going to say. Then that means that the angle that I've chosen, wait a minute, I got to back up. First angle here, very first one, before I drew this one, pretend I haven't drawn that yet, okay? This angle right here is 0. So that means that I'm on an angle of 0 right here, and the sine of 0 is the location right here on this circle, and it's 0. You know that the sine of 0 is 0, I hope, because this point is 1, 0, and cosine comes first, sine is second, sine is 0, yeah? Okay, so now I'm going to open this angle up to 45 degrees. And however tall this was right here, you remember that if this is 1, and I'm saying this is 1, so the radius here from here up to here is 1. On this chart that I'm drawing, this graph that I'm drawing, this is also 1, goes right to the top of the circle. And so if this is 1, then the sine of this right here is this length, whatever it is. That's how long, that's the sine of it, because it's going, the sine of 45 degrees or pi fourths is going to be this side, whatever its length is, over 1, which is this side. Yeah? So that means that when my first marker right here, remember this is the theta axis, if I put pi fourths right here, then its sine value is just as high as that thing reached up. Yeah. Oh, get here on time, Cash. What's your problem? I don't care. All right, actually, I asked you, so I guess I'm supposed to care. All right. Anyway, so if this is the 45 degrees, then the sine value, this length right here, is the value of the sine curve if we graph it, which is right there. I put that a little bit high. Okay? The next one, if I'm splitting this up into 8 equal pieces, the next opening is going to be 90 degrees, right? And that we're calling pi halves. So that would be my next theta, and it's exactly the same distance away. That's why I marked these things to be very, very clearly the same thing. Anyway, I'm opening it up to here, and that value is 1. This one over here, if I draw this at the next 45 marker, that's actually 135 degrees or 3 pi fourths. Would you agree? This angle opened up to there. Okay, so this is 3 pi fourths, and it has exactly the same value as pi fourths did. They're the same height, or they should be if I'd have drawn it right. This thing right here comes over here, so it's the same height as this one right here. Whoops. Over here like that. I get back over to here. I'm going to go a little faster now. Get back to there, and the sine is 0 again. And that's at pi. the next one's going to be 5 pi fourths. Because a 4 pi fourths was pi, coming down to that one right there. And it's 5 pi fourths, so that goes here. And that height is just as far down below the x-axis as these were above. So I'm coming right out here to about right there. And then I drop right straight down, and that value is -1 at, that would be 6 pi fourths or 3 pi halves. And then it goes back up. If I were to draw this one, it would be just as far below the x-axis as that one was. So it has the same height as this point right here. And by the way, that was 6 pi half. So this is 7 pi fourths here. It's just as high as this one. And then I return to 2 pi, and it's 0 again. Now, as you know, you can continue on around the circle. If I were to open the next one, which would be 8 pi, that'd be 9 pi fourths here, it would go up just as high as 1 pi fourths did. In other words, it's going to repeat itself. It's called a periodic function. And then this one would be up to here, and the next one would be down to here. And I could even go backwards. If I started with this direction, then, and I realize I'm out of space here, but if I went the same distance back here as these were out, maybe about right there, then this one would be down to here. And the next one would be down to here. And the next one would be up to here. So it just continues like that. But what I want to draw, or what I want you to see, is what's called the first period of the sinusoid. Or just the, not sinusoid, but just the regular sine curve. And it's not very well drawn because my marker's really slick and this is a really big graph. But it would continue like this. And it would continue over here like this. And that's where your sine comes from. It comes from the unit circle and the size of the vertical leg every time you go 45 degrees. Now, we could have done the 30 and the 60, and we'd have had a little mark here, right here, and another one up here. It's not necessary to get this thing drawn. And you won't see this, what I'm about to show you, in the book. They want you to just plot a whole bunch of points or very, very carefully graph it or copy it off of your calculator or whatever. You're going to be doing a lot of hand-drawn graphs today. And so there's a few things about this graph that I want you to notice. First of all, I only require that you graph one period, regardless of what the instructions say. One period is enough because if you can draw one, I assume you can extend the idea beyond that. That's my assumption. Nice. Another one. You need to go to the office and go get it because I'm not going to excuse you on the computer.
Okay.
All right.
What do I need to get?
Tardy admit so that they know you're tardy and not absent. Okay. There's several things that like I said, that I want you to notice about this, and then I'm going to erase it and show you how I would have done it from scratch without all of this unit circle and stuff. I just want to show you what it was generated from. First of all, what is the actual decimal size of this if the radius is 1? What is this number right here? Or 45, 45, 90? Root 2 over 2, which is about how much as a decimal?
It's like 0.7.
0.707, right?
Yeah.
Okay. So this value on the x-axis right here is 0.707. Now, I realize I'm asking you to estimate pretty grossly here, but if you're going to put this stuff down and do graphs fairly quickly and accurately, and they are really pretty if you do them the right way, we're going to assume that that's about 3/4. So when I'm talking to you about a graph that we're putting together rather quickly, I'm going to say, okay, we start here, we go 3/4 of the way to the top, we go to the top, we come down 3/4 of the way. Then we go to 0, we go down 3/4 of the way to -1, we hit -1, we go 3/4 of the way up. That's what I'm talking about, is this 0.707. It's a rather gross estimate, but if we're hand drawing it, it's close enough. You see what I'm saying? But you, in your mind, are thinking 0.707. 70%, 75%, they're close when you're estimating where things belong on a graph. So we're going to say 3/4 about, and that's what gives it the bend. If you went just halfway up through this point, you'd have a straight line. It would be a zigzag. This is what gives it the bendy part of the curve side, is that you go up on the first one up, you go up about 3/4 of the way. Okay? You okay on that? Also notice that the marks on here, I have 8 of them because there were 8 45-degree angles going around. That's what I recommend you do when you go to graph this. So let me show you how I would graph the sine curve, knowing what I know, without having all of this up here. So I'm going to erase this. We're going to draw just plain old sine from scratch without this unit circle. I just wanted you to see where it came from. And if the objective was nothing more than just a sine, no other transformation, just sine x. It said graph sine x. I would start like this, and I would stretch this out quite a little ways. I don't know, a ways. And I would put a 1 on the top here, knowing that's as high as it's going to go, and a -1 about the same distance down here. Just eyeball it. It's good enough. Then I would just arbitrarily put a point out here, right there. That's what I'm going to go to. Then, once you've decided that arbitrary distance out that you went, now cut that in half. And you can eyeball it. You guys are pretty good at this. Cut that in half. Cut that in half. That's going to be my pi-4. So cut this in half. I'm going to have another one there. Cut that in half. Cut that in half. And this in half, so you've got 8s. That was not very good half. Okay? Then decide how long the period length is. We're going to discuss that very shortly here. But for right now, the period length is just 2 pi because that's when it begins to repeat itself. It goes up, down, and it stops right here. And if it were to continue, it would go up, down again. So this is one full period of the sine curve. Then what I do is I cut this in half and put it down here. I would be right there. Whatever this is, and it won't always be 2 pi. Whatever it is, I cut in half and put it there. Then I cut that in half and put it here. And then I put it here, and that will tell me what I'm counting by. I'm counting by 4ths. So I cut it in half, cut it in half, cut it in half. When you've got this one marked, whatever that is your counter. So here's 1 pi-4, 2 pi-4, 3 pi-4, 4 pi-4, 5 pi-4, 6 pi-4, and 7 pi-4. So once you get to here, after you've cut things in half 3 times, or I think it's 3, cut it in half, yeah. 3 times, then that's going to be your counter. And then you just keep going up and reduce your fractions as you go. If they need reducing. Does that sound reasonable? Once you've got that done, you've got the bulk of it done. You've got the hard part done. Now you do this. Okay, I'm going to start here. I'm going to go 3/4 of the way up. I'm going to go all the way up. 3/4 here, down, down, back up, and right to there. And then you connect them. And if you've done this fairly reasonably, it'll be a pretty good looking graph.
So it's not like the pi-4 increments. You have to change how far you raise up and stuff.
Yes, you're going to have amplitudes. You're going to stretch it. You're going to shrink it. You're going to stretch it this way and shrink it. You're going to move it up and down. You're even going to move it side to side, which is kind of rough. I'll get to that point. Get to that right there. But you guys all know how to recognize the transformations, I think. We just need to figure out how to make it fit with this. And they have different names for the transformations when you're talking about it. You need to become familiar with them. Before I do that, however, I want to show you how to graph a cosine curve. And I'm not going to draw that unit circle back up here, but it is related to it. So I'm going to put a cosine curve up here for you so that you've got a sample of both. And at that point, you can take a picture if you want, or just look up this YouTube video, or just remember it. So if the objective is to graph y equals cosine x, every place sine was 0, cosine was 1 of sorts, wasn't it? And every place that sine was 1, cosine was 0. Remember that? The 1, 0 on the quadrantal angles, they switch places? Okay, so same thing then. I'm going to go once around. I'm going to lop this off over here. This is going to be 2 pi. I'm going to cut it in half, in half, in half. And this would be pi. This would be pi halves. And this would be pi fourths. And you're going, well, it's always going to be that. No, it won't. These are just the regular ones. Okay, so I've got the 3 pi fourths and so forth. I'm not going to label these all out. Cosine starts at 1 because sine started at 0. And now don't think about it like this. I'm going to go 3/4 of the way down. No, you still go 3/4 of the way up because isn't sine and cosine at pi-4ths the same? Isn't it root 2 over 2? Because it's a 45, 45, 90 there, right? So even though you're starting at 1, don't think, okay, I'm going to go 3/4 of the way down. You don't go 3/4 of the way down. You still go 3/4 of the way up. That's one place that they share, right there. And then it will come down to here. And then at this 3/4 marker, it's going to come 3/4 of the way down to -1, just like sine did. Then all the way down, then back up to here, 0, 3/4 of the way up, and back up to 1. And it looks, oops, sorry about that. Oh, that was pretty crappy, man. I'm doing terrible.
It's okay.
When it's on paper, I do a lot better. This is hard to do. Not like that, okay? And this thing, I don't know if it'll help you remember. It's just something that I always notice when I draw this. It looks just like a dessert cup that my mom has at home. She has a whole set of them. We used to have it for family and leaving along when she would serve things up. This little, and it was just little. There was little serving bowls. They were about this big around cups, just great for ice cream or Jello or whatever. Looks like a dessert cup. Whereas this doesn't look like that at all. It's more like just a regular wave. Anyway, this thing would repeat itself just like sine does. It would come back down and go like this. This thing, if you think about it, where this thing starts. I mean, this, if I started right there, would it start and begin to look like a sine curve if I started right here at this big fat point? And if I start, and this thing right here, then from this right here, at 2 pi, this thing would begin again. So sine normally starts here, but if I push it back to here, it looks just exactly like it. So we say that cosine is a pi halves shift of sine to the left, so it would be plus pi halves. So I guess what I'm saying is this, that the sine of x is the same thing as the cosine of x plus pi halves. Take the cosine, shift it back pi halves, you've got the sine curve. Okay, or not? Yeah, okay. If we were to draw a sine on top of this, it would look like this. We'll come back up to here. So that you can kind of see how they fit together. This would be the sine here, and then up, and then back down, here, 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 back up to here, and back up to here. So this is what sine looks like on the same graph with cosine. And if you're in radian mode, whoops, I shouldn't have it like that. If you're in radian mode in your calculator and you set your graph to go from 0 to 2 pi for the x's, this is, and put them both on that, that's what you look like. It's just looks like somebody just took the sine or the cosine curve and backed it up. No, I guess the sine curve is too. Took the sine curve and backed it up here. It would start at 1. So they're both pi half shift of each other. Now I'll talk to you about the other transformations. There were 6 transformations that you guys knew about. There were right, left, stretch, shrink, reflect, reflect. We will not be reflecting over the y. So that one's out. It will reflect over the x. That's easy. Okay. But let me start putting some transformations up here, and you need to get used to the vocabulary. There's a unique vocabulary that goes with transformations of sine and cosine. Well, all trig functions. No, that's not true. Sine and cosine in particular. If you vertically stretch it or shrink it, you're messing with what's called amplitude. The amplitude of the 2 that you've seen so far has been 1. Amplitude is the distance, no matter where it is. I'm not even going to put it on a grid. This what it is. You have the cosine or the sine curve going like this. If you draw a midline through it, like this, so that it starts, yeah. If you draw a midline through it, that would be like the x-axis. If you put the y-axis here, that would all fit in there, right? Whatever the midline of the curve is, from there to a peak, or from there to a valley, and I don't care which direction you go, it is always positive. We will call that little a. And so the amplitude, when they ask you to do that, the amplitude is the absolute value of a. No matter which way you go, whether you go up to get to there or down to get to here, it is a. It is the distance from the midline to a peak or a valley. Amplitude. Okay? You good with that?
Okay, so that midline would normally be the x-axis.
Yeah, if you hadn't moved it up or down anywhere. If the midline is at 15, then you're going to have to add 15 at the end because that's how far you are up from the x-axis. You know what I mean?
Yeah.
So this, right, the amplitude we're talking about is a vertical stretch or shrink. But you were just talking about as a vertical move of some kind. If the x-axis is, if the midline is not at 0. Now you're talking about a move. We'll talk about that in a minute. But this is a vertical stretch or shrink. That's what we refer to it in general with other functions. Vertical stretch or shrink is the amplitude. And it is the absolute value of a. You'll see where this all fits in just a minute. The A and everything else. There's a B and a C and a D. You'll see it, and I'll put it all together for you. Okay. If you want to take this curve that generally ends at 2 pi and squeeze it or stretch it, that's a horizontal thing, right? That has to do with what we call the period length. Okay, and the period length is going to be 2 pi over b, period length. Maybe I should put the equation, the general equation up so you can see where these things fit into a function. So this accounts for all the moves of, let's say, sine function. All you have to do is insert cosine where sine is, and it's the very same thing for cosine. You just have to remember they're slightly different in shape. Cosine starts at 1 and goes down. Sine starts at 0 and goes up without any embellishments to it. But this is what you would get. It's called a sinusoid. It would be a sine of b times x. Well, I better write it this way, then I'll show you the other version of it. B x minus c plus d. I already talked to you about a, and it's sitting right where you would think it would on a function. To vertically stretch or shrink it is a multiplier on the front before the functioning occurs, right? Recognize that? And the sine, S-I-G-N, the sine of a will determine if it's an S-I-N function, whether first or comes down. If a is negative, you'll go down before you go up, because that will reflect the whole thing over the x. You follow me? The sine on a, S-I-G-N, on a will determine whether, if this is your y-axis coming down through here, if it's a negative a, you will start down before you go up. That'll reflect it. Okay. Leave that there. I don't have to put any more about that. Okay. All right. This thing right here in front of x, the coefficient on x, you've learned to call that a horizontal stretch or shrink when you multiply x by something, right? It's always the opposite of what you think. If this is a 2, it's a shrink of a half. Right? If it's a 7, then it's a, if it's a 3/5, then it's a stretch of 5/3. You following me? You remember? Okay, that's what we're talking about here. 2 pi over b, because the period for an unstretched or shrunk horizontally, an unstretched or shrunk sine, its period is 2 pi, so it's got to be some fraction of 2 pi. If b is 3, then it's 2 pi thirds. That's how far out you go. If it's 1/3, then it's 6 pi. Because if b is 1/3 sitting in front of x, then you got to turn that over. This has to do with horizontal stretches and shrinks. We call it the period length. It's a special name for this. Amplitude is a special name for a vertical stretch or shrink. I'll show you how this all comes in a minute, but that's where that number, that's where you're going to get that number from. So coefficient on x inside the sine. This thing right here, of course, is going to have to do with what we call a phase shift. You would normally call that a horizontal move. On a regular function, we call it a phase shift. And this guy, believe it or not, we just say up or down that amount. We just move it up or down. They don't have a real name for it. Phase shift, we call it a PS, phase shift. The phase shift is going to be a lot easier to read with a different version of this. And they give this different version in the book a little bit later in the section before the exercises. But I'm going to give it to you right now. This is very much, it's exactly the same thing, but it's much easier to read for a phase shift. X minus C over B. In other words, if you factor that B out front so that X stands alone, then whatever's back here is your phase shift. Remember I taught you to read it like that before? If you've got a coefficient on x, you want to get that out of there so this stands alone. Whatever you add or subtract, it's going to be the phase shift, and it's C over B. So I'm just going to say the phase shift is C over B. I wouldn't memorize that if I were you. I would just factor that out so you can read it directly. I would. So let's do 2 or 3 of these with this stuff in it, and then you should be ready to go. This you will not get unless you experience it yourself. So we're going to do several examples here. Would you look at example 2? Let's go ahead and graph what they tell us to do. It's got 2 things going with it. Actually 3. 3 transformations. And I'm only going to do the B part. Let me show you how I think about it. The B part says to graph y equals negative 2 sine of x over 3. First of all, remember from algebra, this is an easy remembering, but a lot of people forget it at this point. I don't know why. When you have the statement x over 3, that's the same thing as 1/3 x. Do you all remember that? We have to read that as a 1/3 times x. That's b is 1/3. Y'all read that?
Yeah.
B is 1/3, A is 2. Oh, and I think they wanted us to do -2. You do not say A is -2. A is 2. But the negative says that since it's a sine curve, we will start at the origin. It hasn't been phase shifted at all. We'll start at the origin and we will go down first. That's all that negative is going to do for you. But the amplitude, if they ask you the amplitude is still 2, just 2. It's a distance, and distances are always positive. So this is the first thing that I always do, and you can take a look at this. I've got all of these done the way I want you to do them, so you can use it for a key instead of what's in the book. The graphs for the things you're going to be drawing today are like that. That's what your graphs going to look like. They all look alike, or kind of similar. But if you look at the x-axis, they're nothing alike. And the first thing that I do on all of these, and you can do this too if you want, I write down the function right up here, and then I immediately find I write down for myself all of the transformations. So I can look back and not have to look at that and go, now what did I do there? What? I can just look back at my list, and I can tell, and I can make the graph turn out that way. So this is what I do. I write the function, and I say, amplitude is 2. Reflect over the x. And the period, that one you have to do kind of in your head, or you have to figure it out. But the period on this is going to be 2 pi over b, which is 6 pi. Y'all see that? Or not? Now, the graphing is all about labeling the axes correctly, because once you get the axes labeled correctly, the 3/4, the 3/4 up, all the way up, the 3/4, all that comes in really fast. It's not the point plotting that takes any time. It's getting the graph set up, and that's where I will be grading you too. I don't care if your graphs are really pretty or not. It would be nice if they were, but it's the axes. And it all comes from this stuff right here that you've read appropriately. So I start out like this, and the first thing I do is I take a look at my amplitude. I'm going to have to go up 2. If you want to just leave this one off, so that one line of that piece of paper that I give you, if you just put a 2 here, I'll be fine with it. Down here's 2. Just make sure that you label it properly. I don't care if this distance is 1 on other graphs and 10 on other graphs. Just make sure you've labeled it properly so I can tell that you did it. Get those about the same. That's the reason why I'm going to give you this paper, because the lines are rather wide. And it's easy to just go up 1 and down 1 and label it. Okay? And it's easy to get this correct because those lines are the same width. Then I'm going to come out here and I'm going to put a 6 pi, because that's where it's going to end, and I only require 1 period. Then I'm going to split this up into 8 equal pieces. And then I'm going to do that little thing I told you. 6 pi, halfway back. Is that right here? That's right here. Halfway back is going to be 3 pi. Half of that's going to be 3 pi halves. Good. And half of that's going to be 3 pi fourths. Did y'all catch that? So now you're counting by 3 pi fourths. This is 3 pi fourths. This is 6 pi fourths. 3 pi fourths later, right? Then this will be 9 pi fourths. That'll be 12 pi fourths, which is 3. You with me? See, I'm counting by 3 pi fourths. Next one will be 15 pi fourths. And then 18 pi fourths, but that's 9 pi halves. And then 21 pi fourths, which doesn't reduce. And then 24 pi fourths. That's just to check to see that you landed in the right place. Y'all clear? So this takes the math. You got to be able to split it up. You got to be able to get it, cut it in half, cut it in half, cut it in half. Get to here, count by those all the way up. Make sure these are labeled properly according to this. Then don't forget about this reflected over the x. That comes in when you start to put points in. So the first one's going to go there because I haven't moved it right or left anywhere. Then in the very first one here, I'm going to go 3/4 of the way down to whatever my amplitude is, which is right about here. You following? Goes here, here, and it gets all over your numbers. I agree. Or you write them really small. Here, then 3/4 of the way up to 2. I don't even really care what that is. Just 3/4 of the way up to the amplitude. all the way, 3/4, back to 0. And then you connect them. So plotting the points is not difficult. It's getting, the thing that takes the time is getting your axes numbered properly. So that I know that you read the transformations. And I could look over here and see it, and then I could check over here real quick. This is a really good thing to do because you're always checking back here. Every time you do something new on the graph, check back here and make sure you're doing it right. Like, for example, I put the 2's here because I checked that first. I put the period here because that was down. I did that down here. And then I looked over here again before I start plotting points. Oh, yeah, I got to reflect over the x. Go down. Man, it's about any given moment, there's about 5 of you yawning. You guys need to get some sleep. It's kind of tough when we lost an hour yesterday, right? It's really only 10 to 8. Okay. All right, let's try another one. I'll try and go a little bit faster now that we've got things going. I'm going to do
Doing with everything that we're possibly gonna have.
all right, that one's the phase shift. Are you ready? I don't even know if I have any phase shifts in there. I gave you for exercises. You will have to write a phase shift into an equation, but I don't think I have any graphs for you to do that. We're going to practice a little bit of that now. Writing it based on the words. Okay, so look at example 3. No, we just did that. Never mind. Go to example 4. To the bottom of page 388, example 4. And this one says, write a cosine function as a phase shift of the sine function. We already did that too. We talked about the pi halves, right? Pi halves phase shift. Okay, so I don't really need to do that. Write the sine as a phase shift of cosine. I'm not doing that either. Let's continue. On to example 5. Okay, this one says construct a sinusoid. Now you might think that means draw a graph. It does not. It means write an equation. That's the sinusoid. The sinusoid is the equation. The graph of the sinusoid looks like this. Okay, so when it says to construct a sinusoid, it says put together a function that has these attributes. So it says construct a sinusoid with a period of pi fifths and an amplitude 6 that goes through the point 20. That's a loaded question. That's a lot to do. I'm going to erase this so I got room for people viewing the video. Okay, so this is the thing it's got to have in it. It's got to have a period of pi fifths. What else has got to have?
Amplitude is 6.
Amplitude of 6. That won't be difficult. And it's got to go through
2 zeros.
2 zeros. Got to contain that point right there. Okay, so if the period is pi fifths, then what is B? By the way, is there a phase shift here?
Yes. I have no idea.
This is the phase shift, and we'll build that last. This is going to move the thing so that it goes through this point. Okay? We're not going to have to graph it. Thank goodness. We could look at the graph and make sure it does that with the calculator, but we're not going to have to graph it by hand. This will be the phase shift. I want to build this first. What if that's the period? What's B? This tells me, first of all, this tells me that A is 6. What's B?
Wait,
10.
Could be. It probably is. What you have to say is, okay, well, the period is pi fifths, but the period is equal to 2 pi over B. I want B, so I put in for P, I put pi fifths. And I do a bit of solving. 2 pi over B. You see that's got to be 10? Or you could cross multiply. Pi B equals 10 pi. Divide the pi's, B is 10, just like you said. You can figure it out from here too. If pi over 5 is here and 2 pi over something's here, it's got to be 10 for them to be equal. However you do it is fine. But B, from this right here, that implies that B is 10. You have to actually solve something, the period equation. Then, so what I'm going to do now is I'm going to write the sinusoid without this and see if I can figure out how to fit it in. It's going to be kind of rough, but watch how it goes. I'm going to leave this alone for right now and just write this. Just this information is going to be y equals 6 sine of, anybody? 10 x if x is your angle, or 10 theta if theta is your angle, whatever it is, because that's what we decided B was, and B is the coefficient on x. It gave us the period, But using the formula P equals 2 pi over B, we're able to find out that B is actually 10, and that's what actually goes in the equation. Now this sinusoid right here goes through the point 0, 0, doesn't it?
Yeah.
If we want it to go through the point 2, 0, what do we got to do to it?
Move it to right.
Right 2.
Oh, yeah.
To make it go through 2, 0? Does that make sense?
Back down.
Do we need me to show you what I'm talking about?
Yes.
No,
It's got to go shift to the right too. How do we make that happen up here?
minus by 2, but that's,
You can't just subtract 2 because of that 10.
Gummit,
No.
freaking 10.
Is
oh,
that
you gotta
right?
put, right,
Well,
put that
the 10
x
is
minus
x
2
minus
over
2.
10, so it'd be like x minus 1/5.
What?
You just got it.
People, let me remind you, when you have a phase shift, the easiest way to write it and deal with it is this way in general. Y equals A sine B times X minus the phase shift,
Yes, that's what I was trying.
right? Yeah, I know that's what you're trying to do, and that's what you were saying too. So to make that apply here, it would be Y equals 6 sine parenthesis 10 parenthesis X minus 2, because that will shove the thing to the right too, which is what we want. Close it. Now distribute it to put it in truly general form. That'd be 6 sine of 10x minus 20. That's going to move it to the right too.
Oh, that's the roughest part of the lesson. That's not too
Okay,
bad.
so on the 2, 0, why did you have to shift to the right too?
Because this one right here, without a phase shift, goes through the point 0, 0. You know, if we were going to graph it, it would start here, and it would go up 3/4 of the way to 6 and all the way up, you know, kind of like that. I want it to start here at 2.
I read that as 0.
I got to shove the whole thing to the right too, and that's, oh, I see. I see. Yeah, no, 2, 0. Gonna go right.
So it goes through 0, because the first point that it has to go through, so that's like.
No, it has to hit the x-axis at 2.
Well, I'm saying like you got the first one, you knew it was 0, because it's the main like.
Because the regular old sine curve always starts at the origin and either goes up or down depending on the thing in front. I want it to start at 2, at x equals 2, which means I gotta shove the whole thing to the right too.
Okay.
And that's what that phase shift is. So this is the correct constructed sinusoid. So when it says to construct a sinusoid, it doesn't mean to graph, it means write an equation with these attributes. These 3. Y'all see that? You okay? Let's take a look at example 6. And we're not going to do example 7. So we got one more example and see if we can fit all this into a real life situation. Example 6 again, it says construct a sinusoid. A sinusoid, okay? That doesn't mean it has to have sine in it. It could have a cosine. Sinusoid is anything that repeats itself like a sine curve, whether it's a phase shift or not. And it could be cosine. I'm not going to put cosine in this one, but it could be. All sinusoids are about cosine and sine. Use either one. Here's what it says. Construct a sinusoid, y equals f of x, that rises from a minimum value of 5 when x is 0 to a maximum of 25 when x is 32. Holy camole. That's not nearly as straightforward as example 5 was. We can still do it, and it's not as bad as you'd think, but yes, we're going to try to construct that. Here we go.
Is the midline gonna be 17? No, I mean 20. Is the midline gonna be 17?
Okay, tell me what it said again. It's going to do what?
Rises.
Value of y equals 5 at x equals 0.
So it's got to go through this point. In other words, unless we see a phase shift, there may be a phase shift. I don't know. So I've got this. It's got to go through that point. What other point? This is a low.
32, 25.
This is a high. 32, 25. From right there, even though you don't know how to do this yet, from right there, it'll be really nice to know where the midline is. Because this one's moving up and down. Where's the midline?
15. Because 25 plus 5 divided by 4.
It goes from a low of 5 up to a high of 25. What's right smack in the middle of that?
15.
15 is the average, right? 5 and 25? 5 and 25 is 30. Half of that's 15. Midline is y equals 15. That is a vertical move up. Because the midline is usually 0. You following me? So we gotta remember that. We haven't done one like this yet, but that's what that's telling you right there. What is the period length? That is halfway through the period.
64.
Is that halfway through the period? Goes from 5. By the time it gets to 32, it is at a high. 25. That's not halfway. That's not halfway. That's only a quarter of the way. Right? The way sine curves are drawn goes up like this. What we have is that this right here is 32. That's a fourth of the way. That's a fourth. That's half. That's 3/4. That's full. So what would it be? 128. Okay. So what?
Well, it's half because you know the lows, you know the middle chunk, right? Because you know the minimum part.
Yeah.
So
Well-
then you add 2 more fourths. So you know half of it.
No, you don't know half of it. You know a fourth of it.
But that's
But
the
you know
low,
the
so
low.
wouldn't it be that lower angle? So from that high to that low?
Because you don't know the beginning, you know the middle section.
I don't want the midline there. That's not what I meant. Sorry, I was drawing something else. Thinking something else. What are you saying to me? Am I screwed up?
So
here?
you have the high and the low, right?
Oh,
And so you have that middle section there, not the ends. So like,
so isn't this at 5 and this at 25?
no, I think the one to the right, the very minimum is at 5. It's the low.
So
Right.
the one you have is 32, and then the one to the right, where it dips down.
All right, look, I'll take this off of here so you're happy. Starts at 5. Right there's 5. This is 25. Am I right?
But it's so
Yeah.
Wait, no,
No,
the
the
midline is
The lower one is 5. That one where you just put the 5 is at 15.
the valley is.
That's
Yeah,
5.
there you go.
You could change.
Okay. So the low here is 5. This is 0. I drew that way down to low.
I should have taken me a little
For you guys don't be confused.
So this is 5.
Yeah,
This is 25. This is the x-axis. The midline is at 15. So that was right on that. And it reaches here at 32, which is halfway through. Period is 64. It takes a long time to talk me into things, because I'm so stuck in my own concept. Period is 64. 64, we all agree on that now? Now that I'm got my brain switched around it. Okay.
How did you do 64 though?
The lows are at 5, the highs are at 25. So this thing goes halfway through a sine period to get back to the 5 before it does that again. So halfway through is 32, all the way through.
Yeah, no, when I hit 32 should be at 25. Because the point's 32.25. Oh, yeah.
So I got it upside down?
We were right
No, there's 32 just needs to move over to underneath the 25.
That's 32.
Yeah.
It
This
is?
means that we were right the first time.
What's the period?
128.
Gosh.
I said 128.
Yeah, the one says 64. Well, actually,
I think when we run it through the period equation, it'll turn out with the 64 that we need, but that's not the period. Let's try it, see. And if they're right, we'll refigure this, we'll rethink this, okay?
And the solution is.
Do you want to try running with it with a 128?
Yeah.
No.
64.
We'll do it. Okay. We'll do it both ways. This feels right to me, and I was almost talked into the 64, but I could be wrong still. Anyway, let's see if we can figure this out. If the period is 128, what's that equal to figure out what B is? What does that equal? So that's 128B in the cross multiplying equals 2 pi, means that B is equal to pi over 64.
period is 64.
Is that right? Did they get B equals pi over 64?
Pi over 32.
They have pi over 32 for B?
Yeah, it says the period is 64. So
Okay.
set 2 pi B.
I gotta read this again.
Yeah, it specifically says the period.
Somebody wants to step up here and straighten me out. Go ahead, if you really know what you're talking about. Come tell me, Casey. No, come up here.
Yeah.
Okay.
You can have this if you would like. You don't have to write if you don't want to. At this point.
So what they're saying is you start here at 5,
Yeah,
that's your minimum.
Yep.
Then you go up to 25.
Yep.
And you go back down, and there, you're back at 5.
yeah,
Isn't that one period?
no,
No, then you go a little further
No, no.
until you're back at the.
no, he's right, It is, that is a power.
Yeah, Casey,
No, it isn't. Isn't.
Why is that one?
It is.
Because it's a 5.
It is, because if it starts here, I mean, if we were to start here, if this were the midline, like the x-axis, it would go up, down, and up. So that is one. So that means if I backtrack to there, that would be the
Yeah, Casey.
yeah, that's correct. That's right. When it comes back down to where it started, that it starts over. Yep, he's right. That's good. Good job. I think I couldn't see it because it was up off the x-axis. I couldn't tell. Couldn't see it. Okay. Well done. Nice work. Okay. So we all agree now the period is 64. I'm convinced. You're convinced. You probably were before I was. That's, again, I'm not taking this fast for granted. Okay, so now we have the period, or the B, we have the A. Do we have the A? What's A? 10. A is 10. Do y'all understand where that came from?
Yeah.
Okay, so we can write this much so far. We can write y equals, to construct the sinusoid, we got y equals 10. And then sine, I'll go ahead and use sine. It's where it starts, down here at 5. Then what? Is there a phase shift?
No.
There is no phase shift because all we did is move the start point from 0 up to 5. Right? So it's just going to be B, which is pi 30 seconds, x, that's your angle, plus the midline.
Wouldn't it just be +5?
No, because the midline is.
Midline is at 15. The x-axis has moved from 0 up to 15. This I am sure of.
Oh,
Yeah? Everybody good?
And why is there no phase?
Yeah, wait a minute. Should be cosine. I can take care of the phase shift with the cosine.
Yeah.
And if cosine's going to start below the midline and head up, it's going to have to be negative. Because cosine either starts, if you remember what its graph looks like, either starts here and goes down, or it starts here and goes up. And this one starts here and goes up.
Oh.
And if it starts down at -1 or some version of -1 and goes up, it's cosine. But since it started at a negative, you have to flip it over the x-axis.
Wait, so is it sine if it goes through that origin?
It's sine if it starts at the midline.
Oh, that rules straight away.
I think that was part of the problem.
Now turn the page, and all of those things are correct now. That's a lot of work. I don't know. Obviously, written with mistakes. If you think that I don't make them very often, that's. I screwed that up pretty good. Okay, for the graphs that you have to produce, I have this for you. You can look at that and see if you're right. Regardless of what the instructions say, you only have to graph one period every time. Just make sure that your axes are numbered appropriately when you have to do a graph. And then I have some other ones here for you to look at solutions, because these are the ones that are most often missed. I'll leave them here in my book. You can look at the book for other answers too, but those are the ones that most people want to see. You do not have to do it on this, but you may have one if you think it will be useful. You can do it on your regular paper if you like. So I will leave it here. Get it? It fits in your book if you fold it in half. Oh, that's right, I just pulled it apart. I did. Anyway, there you go. If you want to use that, it's great. If not, it's fine too.
Actually, that's.
Are all the problems just gonna be grabbed?
Do you wanna grab you?
Sure.
Are all the problems gonna be what? What was the question?
Are all the problems just gonna be grabbed and thrown?
No. That's only the first little bit.
Oh, dude, it's.
Then there's gonna be some construct a sinusoid based on things like you just saw. Might wanna go back to that example. There's gonna be all sorts of questions asking about this. You gotta extend your thinking a little bit, see if you can figure it out. That'll be the basis for you to get things going on. Hope that was helpful. Bye.